All right, next one was on heat transfer number 2. I tried to use the reference handbook formula where it's asking for hot, cold side inlet outlet temperatures. When I sketch this problem out, the hot side versus the cold side seems counterintuitive. Normally, the condenser cooling tower side would be the hot side, and the chiller is the cold side. When I worked out the problem, it appeared the hot side is on the chilled water side. Why is this? Yeah, it's a great question. So, and I love how you asked this and provided a picture to kind of say, like, all right, here's option one, option two. One way, I get this negative value out, which doesn't make sense. So I do it the other way, and it comes out to be a positive value, which is the correct answer. So that must be the right setup. But intuitively, it doesn't make sense why that would be the right setup, because how is the chiller, the chilled water side, the hot side, and the condenser water is the cold side? Like, how can that be? And it is counterintuitive, but your picture is perfect and it points to exactly why this is the answer. And I'll kind of back up a little bit and just talk about chiller operations and the condenser water loop and how those interrelate in normal operation. And then we can talk about water side economizer. So normally, let's say you have, and I'll kind of bounce back and forth between your picture. So, no, well, we didn't draw the chiller, so we got to draw the chiller. You've got your refrigeration loop. Here's your evaporator, compressor, condenser, water-cooled condenser, and then expansion. And on the other side of the condenser, we have the condenser water. So let's say this is the refrigerant flowing this way. And then I don't know if it would be counterflow, but suffice it to say, on the water side, we have the condenser water supply. I guess we would call this supply, and condenser water return. And then this goes to the cooling tower. So we got to draw the cooling tower. Condenser water return goes to the cooling tower, and that's going to get cooled off. So that comes into the header, down the fill, drips down, cools off, and that becomes condenser water supply. Somewhere there needs to be a pump in there, but forgive me for skipping the pump. So this is condenser water supply, condenser water return. And then the chilled water, which I didn't draw, is over here on the evaporator, coming off the evaporator. It's also a water-cooled heat exchanger. So yeah, so these are like both shell and tube heat exchangers where you have refrigerant in one and then water in the other. And we're just using the refrigerant cycle as a medium to pass heat through as it goes into the chilled water and then into the refrigerant and then out to the condenser water. So there's a similar loop here for the chilled water. This guy would be going that way. So we'll go this way, coming down. So now this would be chilled water supply going here and chilled water return coming back. All right, so let's put some numbers on this. That'll help us. In normal operation, whether it's summer, winter, pretty much all the time, if you need to do air conditioning, 24 hours a day, 365 days a year, you always have to have good cold chilled water supply available. Maybe your chilled water supply set point for your building is something like 50 degrees. And it always has to be 50 degrees. You can't do air conditioning with, maybe you go 55, but you can't go much more than 60. So supply temperature, and that's not really negotiable. And then let's say there's a 10-degree delta T on the chilled water side. So it should be an R, chilled water return. So maybe the chilled water return temperature is 60 degrees. And then on the condenser water side, this is going to be hotter, right? Because we're using the phase change of the refrigeration system to transfer heat out of the chilled water and into the refrigerant through the evaporator, and then out of the refrigerant and into the condenser water through the condenser. And what are those operating temperatures? Maybe it's something like 80 degrees on the condenser water supply, 80 degrees maybe, and 90 degrees on the return if it's a 10-degree delta T. And I'm making these numbers up, so don't get too attached to these, but this is a kind of a hypothetical situation. For a typical operation in the summer or maybe in the shoulder months when it's hot enough outside that you're not able to use water side economizer, you have to run the chiller. You have to do mechanical cooling. This would be the setup. So what is the hot side? What is the cold side? The condenser water is definitely hotter than the chilled water. That's intuitive. So how could there ever be a situation where we use a plate and frame heat exchanger in place of the chiller and reject heat directly from the chilled water to the condenser water? Let's draw now our plate and frame heat exchanger. This is going to replace the chiller. We still have the same conditions on the chilled water side. So now I'll draw those like this. We have our chilled water return coming in at 60 and leaving at 50 because it has to. And then on the condenser water side, what's going on there? It has to be colder if we're going to reject heat from the chilled water to the condenser water. Condenser water has to be colder. So maybe the condenser water supply is 40 degrees and the condenser water return is 50 degrees. If it's a 10-degree delta T. And you may say, well, how in the world are we making 40-degree condenser water? It's very cold out. That's how. So it's only because it's winter that we're easily able to make very cold condenser water. And then these plate and frame heat exchangers, they have a very small approach. So you can get I mean, I made these numbers in impossibly small approach. So this isn't a very good example, but you can get the condenser water return temperature to within like 1 or 2 degrees of the chilled water supply. So you could and it's also parallel flow, so it's kind of like this. So the leaving temperature of the cold stream, you can't get it quite this close, so it would have to be like 49 and 50 or 51, something like that. You could get this down to 51, and this would be 49. Like 1 or 2 degrees, that's possible with a plate and frame heat exchanger that's very clean. The heat transfer is incredible, and it's parallel flow, so they can get very, very close to one another in that operation. But the key principle is that in winter operation, when you're on water side economizer and you're using the plate in lieu of the chiller, you're actually able to get condenser water that's colder than your chilled water so that your chilled water is the hot side and heat is being transferred from the chilled water to the condenser water, which is not typical. It's a winter operation for a water side economizer. So coming back to your picture, it is option 2. And these numbers are good numbers too. All right, 46 and 48. So they're getting within a couple degrees of each other, which is very possible. Great question. Anything else on that related to that?